Hey, this is part 2 of my lecture series on volcanoes. In the last part, hopefully you've all watched that, we reviewed igneous rocks and talked about the various products of volcanic eruptions. In this video, I want to discuss the architecture of volcanoes, how they erupt, what features they form, what type of structures they develop into, and that sort of thing. So you can see here that volcanoes can take many different forms. They can be the kind of stereotypical upside down cone shape like you're seeing on the left with lava spouting from a central crater, or they can take this fissure style like you're seeing on the right, where lava is flowing out almost like a curtain along a long axial ridge, and that's what the photograph underneath shows. If we go back to kind of that first, more stereotypical example, it's very common for volcanoes that form a kind of conical shape to develop a crater at the summit. And so the crater is kind of the hole at the top of the volcano from which the lava and volcanic debris is vented. But over time, as the magma chamber that's underneath the volcano empties during an eruption, the volcano can collapse on itself because you're effectively moving mass from underneath the volcanic structure to the surface of the earth during the eruption. And when you remove that mass from underneath, that can cause the volcano to collapse. And then the summit area of the volcano subsides and turns into what we call a caldera. So this is the formation of a caldera over time. And so most volcanoes that have been around for a while and have had multiple eruptions develop calderas at their top. This is perhaps the most famous caldera to us locally. This is Crater Lake. So you'll note that Crater Lake, the national park in Oregon, which is part of the Cascade continental arc. So these volcanoes are developing above a subduction zone, and Crater Lake is one of these volcanoes. And you can tell from my description of what a caldera is that Crater Lake is actually misnamed. It should actually be called Caldera Lake. So this is when the volcano underneath Crater Lake collapsed and subsided, filled with water, and then there's been some resurgent volcanic activity that's produced this resurgent dome here in the middle of the lake. There are three fundamental types of volcanoes: shield volcanoes, cinder cone volcanoes, and stratovolcanoes, which are sometimes called composite volcanoes. I'll explain why in a moment. This is an overview figure from your text that's showing these three different types of volcanoes. On the top left, you've got shield volcanoes that produce these very low slope structures. So shield volcanoes are called that because this low, gentle slope that you see here, I'm just going to sketch it in green, looks like an upside down warrior's shield. Over here, we've got the cinder cone. Cinder cones tend to be very small, so note the scale here, only 100 meters. So cinder cones tend to be very small and very steep-sided. In the bottom, we've got a composite or stratovolcano, and so it's made of many, many layers of different lava flows and eruptive ejecta. Mount Fuji that's shown in that picture is a classic composite or stratovolcano. So the different types of volcanoes that I've described form in different parts of the earth. So we've discussed where in the earth you can make magma, which of course is a requirement for having a volcano. But depending on how that magma is made, if it's made through decompression melting at a mid-ocean ridge, for example, versus flux melting at a subduction zone, you might produce a different type of volcanic structure. So this is a really cool figure also from your text that shows volcanism all over the globe and color-coded based on these different magmatic environments. So for example, the big composite Mount Fuji is over here and it's labeled with C and I, and that's because Japan is one of these funny places where there's been so much island arc magmatism that we've actually created new continental crust there. So it doesn't really matter for our purposes right now which you want to call it. It would be considered a subduction zone style volcanic arc volcano. And that's very different than, say, a volcano that you might see as you're driving through the Mojave Desert out here, which would be an R, a rift style volcano. Those rifts tend to make cinder cones, smaller volcanoes, although you can get really big ones, big shield volcanoes, like you get in the East African Rift over here. Continental and island arcs tend to make composite volcanoes. I'm just going to abbreviate that, comp. And mid-ocean ridges and hotspots, those tend to make shield volcanoes. So let's look a little more closely at one of these shield volcanoes. Again, you can see this kind of very gentle sloping, upwarped structure that looks like an upside down warrior's shield. That's where it gets its name anyway. You've got the caldera in the center, and right now there's, according to this picture, there's an eruption that's coming down the flank of the volcano here. And you can imagine this structure building up over many, many repeated eruptions of very runny, low viscosity mafic magmas. So shield volcanoes always form in places where you're getting lots of mafic magmatism. So it makes sense that that would happen at hotspots and mid-ocean ridges, where you're basically pulling apart the crust and allowing hot ultramafic mantle to partially melt and make mafic lava. Another example of a shield volcano, only this time not from Hawaii, but from Iceland. Iceland is a pretty special place, in case you didn't realize this. Iceland is somewhere where a mantle plume, like you have in Hawaii, coincides with a mid-ocean ridge. So Iceland is actually sitting right on top of the mid-Atlantic ridge. We can trace that in the bottom left image here. So here comes the mid-Atlantic ridge and does something like that. And look, right smack dab in the middle of the mid-Atlantic ridge is Iceland. And Iceland is there because, in addition to being on the ridge, most of the mid-Atlantic ridge is submarine, of course, there's a hot spot there. And so that produces lots of volcanism that can build up these subaerial shield volcanoes, just like you get in Hawaii through repeated eruption of basaltic lavas. Cinder cones, again, most commonly form where you have continental rifting. So this is where continental lithosphere is pulling apart. And when that happens, you get decompression melting of the mantle, which produces mafic magma, which, if depending on the extent of the rifting, can make its way to the surface and erupt to form these cinder cone volcanoes. So again, they tend to be quite small. You could probably walk around this cinder cone in an hour or two, for example. Like a person might be down here. You could walk around one of these somewhat quickly. They tend to be very steep-sided, and these cinder cones are something that you can see if you drive up 395, like you're going to Mammoth. You can see them all over the Mojave Desert and parts of the Basin and Range in western North America. And all of this black stuff that's coming out here like this is a basalt flow that would have come out of the cinder cone and flowed over the desert floor. Okay, and then of course last we've got our stratovolcanoes. And perhaps I should be better at calling them composite. It's a better name in some ways because it does a good job of describing what it's made of. So something that's a composite is made of different parts and pieces. So in this case, the volcano is made of stacked lava flows, which are these darker colors. So if we look at the legend over here, the lava flows are these black things here. So I'll just trace a couple of them in yellow. And then the tephra. So tephra is a word that simply describes collectively all of the pyroclastic debris that can come out of a volcano. So it would include ash, lapilli, bombs, cinder, all of that stuff. You can get tephra accumulations. So you can think of these as being probably tuffs. Remember, tuff is the rock type that develops when tephra or glass and lapilli become buried and compacted. And that's what's shown here in all of the kind of pale grayish brown. So you can see that the volcano is a composite of lava flows and tephra deposits mixed with some chunks of kind of pre-existing basement in there. Pretty cool. And I should mention that composite volcanoes typically form above subduction zones and can be very large, like think Mount St. Helens, Mount Fuji style, and they can have huge eruptive, explosive style eruptions. So these are the really dangerous volcanoes that we worry about when we live near them. Here's a photograph taken from the field in a famous composite volcano, Mount Vesuvius, and you can see here that layering or that composite nature I was talking about before, where you have lava layers that are interstacked with pyroclastic layers. And so these pyroclastic layers would be like the tephra layers that we were looking at in the last picture. Okay, I'm going to leave it there. I hope that this gives you the information that you need to successfully complete your second problem set. Go work on that now.